Hi, I'm John Tibble. I'm a junior in the College of Engineering and majoring in computer science engineering. I'm here to talk about the research I've done in the April laboratory this summer as part of the SURE Undergraduate Research Opportunities Program. Today I'm going to be talking about 3D graphics on the iPod Touch, a system we've implemented using Java and Objective-C. One of the problems we've had in our lab is that if the robot goes somewhere we can't follow, we need a way to command and monitor it remotely. We need a complex and real-time system that gives us information about the robot's surroundings. How are we going to get it? What's the optimal solution? The United States military uses something called the PackBot. It's a small robot driven from one of these. It's a laptop with a monitor inside and 2 joysticks. The problem is that if a soldier's head is buried in this machine, they're very, very vulnerable, and it's very dangerous to use. So this is obviously not an optimal solution. We need an intuitive system to control the robot and receive immediate feedback. We need a way to get insight into what the robot thinks the world looks like. What if we use gesture control on an iPod Touch? What if we could visualize what the robot sees with 3D graphics? Well, let's use an iPod Touch. I'm going to talk about the last 2 of these screenshots later. These are screen captures from our program running on an iPod Touch. As it stood previously, the iPod was sent the raw data from the laser and assembled what it thought the 3D world looked like as it interpreted the data. But what if the user wants to see the data represented differently? We would have to modify and recompile the iPod Touch code, which is extremely time-consuming and dangerous if you mess something up. Let's do something different. Let's let each LCM module, for example, the driver program or the laser program, etc., draw its graphics however it wants, and don't let the iPod Touch see the original data at all. This means creating a standardized protocol for putting graphics on the iPod Touch, the LCM GL Buffer T. This is the header file for the Java implementation of the LCM GL Buffer T. It consists of a time in microseconds, a name, a length of binary data, and then a binary data itself. This is how you would create an LCM GL Buffer T. An LCM GL Buffer T is actually the transport mechanism, nothing more. Before we create one to send to the iPod, we must first create an LCM GL object to issue the OpenGL commands to. And as you can see, it's very straightforward. It's very boring instantiation and initialization, which makes it very simple for the user to implement. It was originally implemented using byte buffers and data streams, where the slightest mistake could result in graphics problems. But this new way is much more intuitive. Now for a quick example. Say we've created our LCM GL buffer message as such, and we apply the OpenGL opcodes to it. We push the matrix, we change the color to blue, we put text in 2D and 3D on the screen. We say, if the robot's position is available to this program, transform our local coordinate space to match it, and then draw the laser on the OpenGL world if it's available, scale the world, color it cyan, draw a box, and end. Now, this is all well and good, but how do we get this to the iPod? Well, let's create our LCM GL Buffer T out of this LCM GL object using the makeMessage function. We pass it the system nanotime and the name we want the iPod to hold on to, and then publish it to our local LCM network, which then gets relayed immediately to the iPod Touch. The results of that code I just described. On the left, you see our simulator used in the lab to emulate different environments and the robot's behavior. The blue triangle you see is the robot's position, and ahead of it you'll see many red dots. That is what the laser would return that's what the laser would return if the robot was in this environment. On the right-hand side, you see the iPod Touch with the blue box representing the robot, and the blue polygon in front of it representing the laser scan. Above it, you can see the text 2D and text 3D displayed in our environment. It's that easy. In a few lines of Java, you can display your graphics on the iPod Touch. If there's an issue with your code, the iPod will do its best to handle the error and let you know what the problem is with an on-screen message. At the moment, we've implemented almost 25 OpenGL opcodes, all the way from changing the color, to vertex arrays, to rotations, scaling, text 2D, 3D, pushing and popping matrices, and as well as some OpenGL primitives not supported in OpenGL ES 1.1, such as circles, disks, boxes, cylinders, and such. We also have a couple of special April Lab specific opcodes called Draw Laser and Transform Pose, which you just saw. Other features. Large and complex graphics are cached on the iPod to save bandwidth and processing time. The system is easily extendable to include 3D models through OpenGL-style primitives. Once you've created a complex model, you can export it as a resource instead of a buffer and save it on the iPod until it's needed again, like the screenshots you saw earlier. On the left, you see our 3D model of our robot with a SICK LiDAR on top, made out of OpenGL primitives, and on the right you see a model of a person, also made out of OpenGL primitives. This system of graphics buffers does not require the iPod code to be recompiled again. The system is robust to having the iPod program interrupted and/or restarted. It's very easily extensible and easy to implement. If you have questions, please check out the April Lab website at april.eeks.umich.edu or email me, John Tibble, at jtibble@umich.edu. Thanks for watching.